This video will discuss logarithmic differentiation and curve sketching. And here's an example. Let's say you have y equals x to the x, and you want to find it. Well, it's relatively easy to do, but notice we've got a function of x as the base, and then a function of x in the exponent. Whenever that happens, neither of the rules that we have for sort of exponential type form apply. Here are the two rules that we're familiar with. We know that the derivative with respect to x of x to the n, where n is just some real number, is n times x to the n minus 1. And if we take the derivative with respect to x of some constant raised to the x power, we know that that's natural log of that constant, or the base, times the original exponential function. But this rule doesn't apply because we have an x value here, a function that varies with x as opposed to just a real number. And then this rule doesn't apply because we've got a function of x here as opposed to just a real number. So you might say, how can I find the derivative of something like this? Well, it turns out we can compute the derivative relatively easily. We're just going to take the logarithm of both sides. And then because one of our log properties, which says that log of a to the n is n times log of a. So you have a power inside that logarithm, you can bring it out front. And this is, of course, where on the domain, or on the common domain, or the intersection of the domain of this function and this function. So we're assuming here that a is positive. And so with that in mind, we can take this x that is in the exponent here, and we can bring that out front. So it turns out that the log of y, or the natural log of y, is equal to x times natural log of x. And while I don't know the derivative of y yet, I can find the derivative using implicit differentiation. So we'll differentiate both sides implicitly with respect to x. And when I say implicitly with respect to x, what I mean is anytime I see a y, I'm remembering that y is equal to a function of x. The y is a function of x. And that's relatively easy to do. You have the derivative with respect to x of natural log of some function. You get 1 divided by that function times the derivative of the inside by the chain rule. The derivative of the inside is dy dx. And then on the right hand side, we've got a first function and a second function. The derivative of that product requires a product rule. We'll get the derivative of the first times the second undifferentiated plus the derivative of the second is 1 over x times the first. And of course, 1 over x times x is just a 1. So we can solve this for dy dx by multiplying both sides by y. And so we'll have dy dx equals a natural log of x plus 1 times y. But then we remember we want our function, or we want this derivative of y with respect to x in terms of x only. We don't want this y here if we can help it. And we can help it because y actually is x to the x. So you can replace this y with x to the x, and you'll have the derivative of y with respect to x as a function of x. And if you remember that y was actually x to the x, what this tells us is that the derivative with respect to x of x to the x is this. And that's called logarithmic differentiation. And we use that whenever we've got a function of x in the base and a function of x in the exponent, because of these two properties. We've got this differentiation rule, excuse me, and this differentiation rule, and neither of them apply. But you might notice that if I tried to apply this rule to this function, and if I tried to apply this rule to this function, I would get something that looks similar to what we got right here. For example, if I take the derivative with respect to x of x to the x, and I try to apply the power rule, that's what we call this. And I'm going to call this exponent rule for a base a not equal to e. But if I try to apply the power rule here, question is the derivative of x to the x power the exponent times x raised to the x minus 1? If I simplify this on the right, I have an x to the first times x to the x minus 1. Since the bases are the same, you can add the exponents, and then we just end up with an x to the x. So it looks like the derivative with respect to x of x to the x might be x to the x. We know that that's not true because that's not what we get when we use logarithmic differentiation. But notice that if I distribute this x to the x to this expression here, I've got natural log of x times x to the x is my first term, and x to the x is my second term. And if I take the derivative with respect to x of x to the x, trying to apply that power rule, I get this just one term right here. Now, if I try to use my exponent rule for bases other than e, then according to that rule, I should have natural log of the base, which is x, times the same exponential. And that turns out to be exactly the same as that term right there. So it turns out that whenever we use logarithmic differentiation to compute the derivative of x to the x, we actually get a sum. We get the derivative that we would expect to get using that exponential rule with for bases other than e, plus the derivative that we would expect to get using the power rule. And you might say, well, why is that true? Now we're in calculus 1. So this is a little bit of a preview of calculus 3. But in calculus 3, you're going to learn about functions of several variables. And this is, I think, in chapter 13 of our textbook. 11 is vectors, just geometry of space. 12 is vector value functions. And then in chapter 13, you learn about functions of several variables. So what we're doing here actually makes sense if we think of this in a slightly different way. Rather than having functions of x only, in calculus 3, we have functions of x and y. And every xy pair is associated with a z. So if we wanted to, we could graph that function. It's usually a surface in three-dimensional space. Here's the x-axis, or coming out of the page. There's the y-axis. So the xy plane is down here. It looks something like this. And then at every xy in the xy plane that's in our subset of the xy plane that is the domain of that function, we associate a point z, a height. And then as we do that, for all of the points xy in the domain of the function, we get a surface. I'll call it a surface S, given by z equals f of x and y. Now, if f of x and y equals some function of x and y, one variation that we can think about is sort of a variation on this theme. I've got x to the x right here. So, okay, well, what if I had a function of two variables x and y, and I was interested in that function x, where the base is x and it's raised to the y power? Well, in calculus 3, we learned about something called partial differentiation. In calc 1, we learned about slope of a tangent line. That's what our derivative gives us. Also, we think of it as the instantaneous rate of change of that function with respect to that independent variable. With partial differentiation, we're talking about the instantaneous rate of change of z. So the output value for this function f of x and y as x changes or as y changes And usually you're thinking of the other variable as constant. So the partial derivative of f with respect to x is sometimes denoted that way. It's not a d, it's sort of a partial sign. It looks a little bit like a delta, but it's not a delta, it's a partial sign. Partial of f with respect to x can be represented with subscript notation as well. Technically, this is the limit as delta x goes to 0 of f of x plus delta x and y minus f of x and y, all divided by delta x. So it's just a change in z divided by change in x, but the y is held constant. And you can tell that it's held constant because we don't do anything to the y values here. We start at x plus delta x, and then we end at x, and we take the change in z as x changes from x to x plus delta x, and we divide by that change in x, and then we take the limit as the change in x goes to 0. That's the partial derivative of f with respect to x. So in practice, I usually don't use this limit definition in practice. We just treat the other variables as constants. And in this case, our function is a function of two variables, x and y. So we're going to treat y as a constant and differentiate with respect to x in order to compute that partial derivative. And this is an aside, it's sort of a preview of Calc 3. Now, if I'm treating this y as a constant, when I take the derivative, I'm going to use the power rule. This rule that we talked about earlier. Bring the power down, multiply by x to the 1 less power. So the partial derivative of f with respect to x is y times x to the 1 less power. And now similarly, if I want to take the partial derivative of it with respect to y, that's denoted that way, or we can use subscript notation. Now technically that's the limit as delta y goes to 0 of f of x and y plus delta y minus f of x and y, all divided by delta y. So again, it's just a change in z as y changes from y plus delta y to y, whereas here we change from x plus delta x to x. But notice that the x's stay constant. We haven't done anything with the x's. And then we divide by delta y. So that's the partial derivative of f with respect to y. And if we want to compute that, you just, well, you're looking at the slope basically in the y direction at that particular location. This is the slope in the x direction at that particular location. So we'll call this slope of the surface. So it'll be at x, y, and z, which is f of x and y. You can find that slope that way. This is the slope of the surface in the y direction. At x, y, and f of x and y. Now, if I'm finding the slope of the surface in the y direction, I just treat x as a constant and differentiate with respect to y. Okay, with that in mind, when I'm computing the partial derivative of f with respect to y, and I'm thinking of my x as a constant, it makes sense to use this exponential rule for bases other than e. So my base is a constant, and I'm differentiating with respect to the exponent, or the variable in the exponent, which in this case is y. So I've got the derivative basically of a to the y. Well, the derivative of a to the y is natural log a. In this case, instead of an a, we've got an x times the exact same exponential. Okay, so we do actually apply the power rule for the partial derivative with respect to x here. And we apply the exponential rule for bases other than e for the partial derivative with respect to y. After we learn these rules for partial differentiation, which give us slope in the x direction and the y direction at a particular location. And if you want, you say, what do you mean the slope in the x direction or the y direction? Well, we could look at this surface. And we could say, okay, let's require y to take on some particular value. So let's say y is equal to y naught. So we're on some plane, y equals y naught. And we're looking at where that plane y equals y naught intersects the surface. Then we say, okay, if I'm at this location, x naught, y naught, what's the slope in the x direction at that location? From this drawing of my surface, it looks like the slope is negative. So I would compute a function by treating y as a constant and then differentiating with respect to x. And then if I plug in that point, x naught, y naught, that's going to give me a number. That number is going to be negative there because we can tell that the z values are decreasing as x increases. So that's the slope in the x direction. The slope in the y direction would be considered similarly. So you fix the x values. Say let's require x to be equal to x naught. So we're looking at a plane x equals x naught and seeing where that intersects the surface. And then you're saying, okay, if I'm on x equals x naught and I let my y increase by a little bit, do my z values change? Is there a change in z with respect to y if I force my x's to be held constant? And I say, yeah, well, certainly there is. It looks like just from this drawing of the surface, the z values seem to increase at that location. So when I compute that partial derivative of f with respect to y or z with respect to y, same thing. And I'm going to get a function of x and y. I'm going to treat x as a constant, and then I'll differentiate with respect to y. And then after we do that, if we plug in the point, we're going to get a number, and that number is going to be positive based on this graph. Looks like our z's are increasing as y increases, and our x's are decreasing as y increases at that particular point for that particular function. Very important to me that my students actually understand what it is they're computing. They understand the geometric interpretation of these objects. So this is what we have for this particular function, x to the y. Now, if we want to, we can compute what's called the total differential of f, or sometimes called the exact differential of f. The total differential of f is denoted by df, and it's just the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. So this is our total differential of f, or the exact differential of f. And again, you'll learn more about this in Calculus 3. But in our particular example, so we've got f of x and y equals x raised to the y power. Then the total differential of f is the partial derivative of f with respect to x, which we computed using the power rule. That's y times x to the y minus 1 times dx, plus the partial derivative of f with respect to y, which we computed using that exponential rule for a to the x or a to the y in this case. That partial derivative with respect to y times dy. You might say, okay, well, what does this mean? What does this represent? This is actually the expected change in z. There we go. Using the tangent plane approximation. Or linearization, sometimes that's what it's called. At a particular point, x naught, y naught. As x changes by dx units, and y changes by dy units. So basically the idea is we've got a surface. We create a little tangent plane on that surface. And we use that tangent plane as an approximation of the surface. We say the surface and this little tangent plane are approximately the same. So what if I take a little step away from my point x naught, y naught to a neighboring point on my little tangent surface? What is the expected change in z given that I'm using that tangent plane as an approximation to the surface? Well, the expected change in c is, or the expected change in f, which is the same thing. Let's remember z is the f of x and y. Z is just the name that we've given for our dependent variable. F is the name of the function. I almost think of z as being like a nickname, and f is sort of the formal name of the function. But we're saying, okay, well, what is the change in f or the change in z if I'm using that tangent plane approximation? Well, it's this expression evaluated at x naught, y naught. That's giving me the slope in the x direction at x naught, y naught times some tiny change in x. That's giving me the slope in the x direction, which is change in z divided by change in x, times change in x. So it's going to give me a change in z at my x changes by dx units. And then here we've got a change in y, or excuse me, a change in z with respect to y, partial derivative of f with respect to y, or partial derivative of z with respect to y, same thing. We evaluate this at the point x naught, y naught, we get the slope in the y direction at x naught, y naught. If we take that and we multiply by a tiny change in y, we get a change in z due to changes in y. So this is change in z as y changes by dy units. And here we're holding y constant, and here we're holding x constant. We say, but what if I'm not holding one of them constant? Well, basically you get the change in z due to changes in x, and then you add the change in z due to changes in y, and then you get the total change in z. And so that is the total differential. It's really close to what we did up here, right? But it's not exactly the same thing. Well, if my y is actually a function of x, I can just take this total differential and I can divide by dx, and we get something that's meaningful. So our df dx, the total, or the change in z with respect to f, where y is actually a function of x. So now rather than having two independent variables, x and y, I've got x, which is independent, and y, which depends on x. Then in that case, what I would have is the partial derivative of f with respect to x plus the partial derivative of f with respect to y times dy dx. So it's giving me the change in f with respect to x, this sort of independently from y. And this is the change in f with respect to y times the change in y with respect to x. So this is the change in f as x changes, but due to changes in y. Or you can call that change in z if you prefer. Change in z as x changes, or excuse me, let's say as y changes due to changes in x. It's a little bit confusing, isn't it? Say it's change in z as x changes due to changes in y, or is it the change in z as y changes due to changes in x? It's kind of both, isn't it? Because they're connected. Y is a function of X. And we know that there's that relationship between Y and X. So I'm not really sure if I should say as X changes due to changes in Y, or as Y changes due to changes in X. But this is a change in Z. As X changes. Let's say when Y is constant, I think. So if Y happens to be held constant, that's what we would get. Not sure about that piece. Definitely something to think about. But given that, if my function f of x and y, instead of being x to the y, was f of x and y of x, that is x raised to the y of x power. Then the change in f with respect to x is the partial derivative of this with respect to x, treating y as a constant. So we use the power rule. We have y times x to the y minus 1, plus the partial derivative of this with respect to y, treating x as a constant. So that we're going to use that a to the x rule. So we're going to use natural log of a base times the exact same exponential times the derivative of the inside. And that is the exact same thing that we get if we take the total differential of f and divide by dx. If I divide here by dx and divide here by dx and divide here by dx, then I just get the total change in z with respect to x. You might be thinking, okay, how is that related to this logarithmic differentiation again? Well, my hope was that you'd see where that sum comes from. If we talk about, I've got having a function x to the x here. Instead of a y of x, if I just had x raised to the x, this would be x times x to the x minus 1, which would simplify to x to the x. And then we have natural log of x times x to the x times the derivative of x with respect to x, which would just be a 1. So that's what we would get if y of x happened to be the identity function x. Then we'd get the derivative of x to the x with respect to x is this. I think that's kind of interesting. You might say, okay, well, what about the derivative with respect to x of some function of x raised to the different function of x in general? Is there a rule for that? Well, there's not a rule for that yet, but we could infer a rule for that, or define a rule for that. I have a feeling we're just going to use those two rules and then add them together. Okay, how can we infer that? Well, let's just say y is equal to f of x raised to the g of x power. Okay, I'd really like to get rid of that g of x in the exponent. So we do what we always do whenever we're trying to get that function of x out of the exponent. We take the log of both sides of some equation. And then we say, because log of a to the n is equal to n times log of a, on their common domain, so when n is, or when a is greater than 0, we can bring this exponential or this exponent in front of the logarithm. Okay, well, what's the derivative of y then? Well, if I want to find the derivative of y with respect to x, where y is actually this function, we differentiate both sides with respect to x. And here we're remembering that y is actually a function of x. I'm going to keep that in mind. With that in mind, when we differentiate both sides with respect to x, use the product rule on the right and the chain rule on the left, or sometimes we just call it using implicit differentiation on the left. Okay, well, what's the derivative of log of a function? It's 1 divided by the function times the derivative of the inside by the change. That equals the derivative of this left-hand side using the product rule. Call this the first function, call this the second function. And according to the product rule, we'll have the derivative of the first times the second undifferentiated plus the derivative of the second function. Well, that requires the chain rule. The derivative of log of a function is 1 divided by the function times the derivative of the inside by the chain rule times the first undifferentiated. Now we can think of this as a product divided by 1. So we can multiply straight across there. We'll just have some exponential expression or some excuse me, a quotient expression there after we multiply straight across. And then we'll multiply both sides by this y of x to get dy dx by itself. So we'll have dy dx equals b prime of x times natural log of f of x plus f prime of x times g of x, all divided by f of x. And all of that is multiplied by y of x. Now, if you want, you can replace y of x with what it is. And I'd like to do that. Remember what y of x is. Y of x is actually this function, f of x raised to the g of x power. When I multiply both sides by y, I can multiply by f of x to the g of x power, and that's the same thing. So if we distribute that now, distribute term by term, this is what you get. Now the derivative of y with respect to x is the g prime of x times natural log of f of x times f of x raised to the g of x plus f prime of x times g of x, and then we've got f of x raised to the g of x, all divided by f of x. You can think of that as f of x to the first. Now, since I have f of x to the g of x divided by f of x to the first, I can bring this up to the numerator. You can just subtract the exponent. And you'll have this. This will be f of x to the g of x minus 1 power. And that is the derivative with respect to x of y, where y was f of x to the g of x. So I guess we've derived a rule. I don't know how often I would use this rule. I could use this instead of using logarithmic differentiation, although I'll probably use logarithmic differentiation every time instead. But what I want you to notice is it is just a sum. It's a simple sum of what we would get if we treated f of x as a constant and differentiated with respect to x where g varied, or if we treated g as a constant and then differentiated with respect to x where f was allowed to vary. And let's look at that. Let's make sure that that's true. If I tried to apply the power rule to this, so what is the derivative with respect to x of f of x to the g of x due to the power rule? Well, if I tried to apply that power rule, where I'm thinking of the power as constant and f is varying, well, I'd have the power times the original base raised to the 1 less power times the derivative of the inside by the chain rule. And the inside function is f of x here. We have an f prime of x. And that is what we have for our second term over here. This is the I'm going to say this is the term due to the derivative with respect to x of x to the n. We apply that x to the n rule to our original function, that's what we get. Similarly, if I take the derivative with respect to x of f of g of x, but now rather than using the power rule, I use the a to the x rule, where I'm thinking of my base as staying constant, and my exponent is varying. Well then, according to that rule, we should get natural log of the base times the exact same exponential times the derivative of the inside by the chain rule, and the inside function here is g of x. We'll have g prime of x. And I guess I should highlight that. Here, I'm using the power rule, so I'm thinking of this as varying. This is my inside function. And here, when I compute the derivative, I'm thinking of this as constant, and then this is varying. I'm thinking of that as my inside function in this case. So I use the chain rule here, and I use the chain rule here, but in this case, I'm using this rule, the derivative of x to the n. And in this case, I'm using the derivative of a to the x. If we add those together, that actually turns out to be the derivative of f of x to the g of x power. I think that's kind of cool. Now you can remember that, just memorize that and then apply it anytime you see a function of x raised to the function of x power. Or you can take the logarithm of both sides and use logarithmic differentiation every time. But logarithmic differentiation does lead to this result. So that makes it nice. And it's, I think, relatively easy to remember that we're just sort of switching our perspective regarding which is a constant, which of these functions is constant, and which one is varying. When we think of the base is varying, and that is constant, we use the power rule. When we think of the base is constant and the exponent is varying, we use the exponential rule for bases other than. I think that's kind of cool. All right. Now there was a particular example that I thought was pretty interesting. I believe it was natural log of x raised to the sine of x. I actually just looked it up. It was actually natural log of x raised to the cosine of x power. Now, before I sketch any curves, I always want to think about the domain of the original function. Now, typically, if I have a logarithm in my function, I want to make sure that whatever's inside the logarithm is positive. If I have even roots in my function or rational exponents, I want to make sure I am not taking the even root of a negative number. So don't take the square root, the fourth root, the sixth root, any even roots of negative numbers. And we also don't want to divide by 0. Now, there's no division, so we don't have to worry about that. But we do need the x values to be positive, and we also need this base to be raised or to be a positive number. We need natural log of x to be positive because we're raising it to the cosine of x power, and cosine of x is a number between -1 and 1. Now, if cosine of x is between -1 and 1, it could be, say, -1/2. We don't want this to be a negative number raised to the -1/2 power, because if we had this base raised to the -1/2 power and the base was negative, well, then we have complex roots or complex answers, and we don't want complex answers. We're interested in this being a real valued function. So if y is real valued, so y is a real number, then the domain of y, maybe I should give it a name. call it f of x. The domain of x is going to be the set of all x in the real numbers such that x is positive and I need natural log of x to be positive. Now, if natural log of x is positive, then we're requiring ourselves to be on the interval from 1 to infinity. And that's because we know what the natural log of x looks like. Natural log of x looks like this. When x equals 1, natural log of x equals 0 because each of the 0 power is 1. We don't want to include x values between 0 and 1 here, because if x is between 0 and 1, natural log of x is well defined, but we're going to have a negative number there, and then we'll be raising a negative number to some power between -1 and 1. And a negative number to a negative power is fine, but anytime we have an even number in sort of a fraction here, like if we had a rational number for the cosine, and let's say cosine was 1/2, if this is negative, well then we're taking these, we're taking that negative number and we're raising it to 1/2 power, which would be a problem. Actually, let me take that back. That actually might not be a problem for us because on the interval from 0 to pi/2, our cosine function is positive. So I'm actually raising this natural log of x to a positive power. But actually, no, wait, we might still have some problems because the y values here are between let's say 0, it's not going to be 0. It's going to be cosine of 1, right? That's going to be the smallest value here. The y values in the interval of interest are going to be between cosine of 1 and 1. And when our y values are between cosine of 1 and 1, we might have rational exponents with even numbers in the denominator. You know, anytime we've got an even number in the denominator on that interval, we're going to have a problem here because then we'd be taking a logarithm of a number between 0 and 1, which is negative, and we'd be raising it to a power where that power would indicate we're taking the even root of a negative number, and we don't want to do that. So, okay, we've thought about it. This is the correct restriction. The domain of f requires that x be positive and natural log of x be positive. Our function looks like this. We're just interested in the x values that correspond to the positive y values, which are 1 to infinity. So, and that's our domain. And if we want to, we can take the derivative of this using logarithmic differentiation, or we can use our new rule that we just inferred. You can take the derivative thinking of the base as a constant, and then you can take the derivative thinking of the exponent as a constant and then add them together. Or we can use logarithmic differentiation. I'm going to use logarithmic differentiation, but then we can always verify that the derivative is what it's supposed to be using this rule. And so let's do that. So I have y equals natural log of x raised to the cosine of x power. And I'm taking the logarithm of both sides in order to use that logarithmic differentiation. And then because of that log property that we've learned earlier in this semester, we reviewed it. You probably learned it in high school as well. Log of a to the n is n times log of a on their common domain. So we'll say where a is positive. Then this is what we get. We have log of y equals, well, if I bring that cosine out front, cosine of x times natural log of x. And when you're doing the computation, you can see that in order to take the natural log of x, natural log of x has to be positive. So our domain does have to be 1 to infinity. Okay, well, what is the derivative of this? Well, if I take the derivative of the left-hand side with respect to x, treating y as a function of x, I have to use the implicit differentiation. So I have 1 over y times the derivative of the inside with respect to x, which is dy dx, equals the derivative of the right-hand side using the product rule. Here is our first function. There's our second function. And then the derivative is the derivative of the first which is negative sine of x times the second, undifferentiated, plus the derivative of the second, which is 1 divided by the inside function, which is natural log of x, times the derivative of the inside, which is 1 over x, times the first undifferentiated, which is just a cosine function. And you're trying to get to y dx by itself, so you multiply both sides by y. So you have negative sine of x times natural log of x, plus if we simplify the product of those fractions, we've got cosine of x divided by x times natural log of x. All of that is multiplied by y, and y was natural log of x raised to the cosine of x. If we distribute, I'll call this f prime of x now because y was actually labeled f. We've got negative sine of x times natural log of x times natural log of x to the cosine of x, plus, if I want to simplify here, I've got a 1 over x and a cosine of x. And this is a natural log of x to the first in the denominator with a natural log of cosine of x in the numerator. Since the denominators are the same, we can just subtract those exponents. This will be natural log of x to the cosine of x minus 1. And you can see from the form of this that this is exactly what we would get using that rule that we talked about earlier. We said, okay, if we think of this, if we take the derivative of this using the power rule, we get cosine of x times natural log of x to the cosine of x minus 1. That's what we have here, times the derivative of the inside by the chain rule, which is the 1 over x. Or if we start here and we say, okay, rather than using the power rule, let's use the a to the x rule. Well, then we're thinking of that natural log of x as being sort of constant. We get natural log of the base times the exact same exponential times the derivative of the inside. The derivative of cosine of x is negative sine of x. So that's the rule that we derived. This is f prime. Now, if we want to, we can factor out a natural log of x, but it's actually relatively complicated to figure out when this function is 0. In order to sketch the curve, we would be interested in where this function is 0. And then any time f prime changes signs from positive to negative or negative to positive, we'd have relative extrema. And anytime f prime has an extreme value itself, or it has a relative minimum or a relative maximum, that would correspond to a point of inflection of the original function. Now, to me, it's not at all obvious when this function is 0. But in order to find the critical points of the function, we would set this function equal to 0 and then solve for x. We're just going to do that graphically on Desmos. I'll just say since it is, let's say, challenging to solve the equation f prime of x equals 0. We'll examine the zeros of f prime on line. And we'll say using a graph created on Desmos.com. And then we can say, well, remember at every 0, if f prime changes from positive to negative, then we'll have a relative maximum. If we're at a 0 and f prime changes from negative to positive, then the original function changes from decreasing to increasing. So we'll have a relative minimum. So then we'll use the first derivative test. Sort of implicitly, we won't make a sign chart, but we'll be thinking about that sign chart. to infer a relative extrema of the function. Relative extrema of f. And then we also know relative extrema of f prime correspond to points of inflection of the original function. Which correspond to the second derivative being equal to 0. And of course, the second derivative is equaling 0. And if we have relative extrema, f prime is changing signs at that location. So f double prime is changing signs. F prime is going from increasing to decreasing. The changes from positive to negative, it's going from concave upward to concave downward. The changes from negative to positive, it goes from concave downward to concave upward. Okay, so we're going to do that. And in order to and make sure that that's actually what we have, that those relative extrema of f prime actually correspond to zeros of f double prime and changes in sign of f double prime, let's compute f double prime. When I compute f double prime, I'll do that using the product rule and chain rule as well. So now I'm taking the derivative with respect to x of negative sine of x times natural log of the natural log of x. And actually, I think what I'm going to do is I'm going to use this form where we had this expression times natural log of x raised to the cosine of x. So I had negative sine of x times natural log of x plus cosine of x all divided by x times natural log of x. All of that is multiplied by our y, which was natural log of x raised to the cosine. So now when I take the derivative of this, I'm going to use the product rule. I'm going to think of this as my first function, and this is my second function. I'll take the derivative using the product rule. What we'll have is the derivative of the first. Well, the derivative of the first requires a product rule for this, and a quotient rule with a product rule inside for that. So using the product rule on this part, we'll call this the first function, and this the second function. We'll have derivative of the first, derivative of negative sine of x with negative cosine of x, times the second undifferentiated, plus the derivative of the second, which is 1 divided by the inside function, which is natural log of x, times the derivative of the inside. That's the derivative of the second times the first. And then we're adding the derivative of this expression. And the derivative of that expression requires the quotient rule. We're going to have, according to the quotient rule, it's low d high. So the bottom function times the derivative of the top function. And the derivative of the top function is derivative of cosine, which is negative sine of x, minus pi, which is the top function. And then d low requires the product rule. So I have some big open parentheses for that. If this is my first function here and this is my second function here, I take the derivative using the product rule, I have derivative of the first times the second. And then we'll add the derivative of the second, as 1 over x times the first, which is just x. And then we're dividing all of that by low, or x squared times natural log of x, quantity squared. So that is the derivative of the first here. And we're multiplying that by natural log of x times cosine or raised to the cosine of x. Derivative of the first times the second plus the derivative of the second, which is actually our first derivative. Times the first, which is just this factor again. That's a lot, but we'll try to simplify. Here, if I multiply straight across, first I'm just going to write that term down. There's not much to simplify there. If I multiply straight across here, I'll have negative sine of x divided by x times natural log of x. And here we will subtract sine of x times x natural log of x minus cosine of x. Or actually, if I factor out that negative, I can make that a plus. Cosine of x times natural log of x plus 1. All divided by x squared natural log of x quantity squared. All of that times natural log of x raised to the cosine of x. So we're taking this expression, and then we're adding this. Now, if you want to, you can factor out that natural log of x raised to the cosine of x with both of these terms and try to combine these. I don't know that we're going to have any simplification. I don't think it's going to simplify. If I squared this, I'd have this term squared, so I'd have sine squared natural log of x squared. I don't think that's going to cancel with anything. And then here, I don't know. It would just take a lot. I guess if we wanted to, we could get a common denominator. Let's try to get a common denominator. So I'll multiply this by x natural log of x, or x squared natural log of x squared, times or divided by itself. And we'll do the same thing here. In order to get that x squared natural log of x squared to the denominator, I multiply by 1 x natural log of x squared. And then here, my goodness, I need an x natural log of x divided by x natural log of x. Then we have a common denominator, so we can add the numerators and then square it. So much algebra. All right. So now we've got, here we'll have negative cosine of x times x squared natural log of x squared times natural log of x minus sine of x times x natural log of x minus another one of those. We actually have two of those. We're subtracting cosine of x times natural log of x, and we're subtracting a cosine of x just by itself. And then here, I've got negative sine of x times x natural log of x times natural log of x, or natural log of x. If I square this expression, I'm going to have that squared in the numerator. So I'll square that, square that, square that, and square that. And then when I have, it's going to be an a plus b quantity squared in that numerator, essentially. So by an a plus b quantity squared, we get a squared plus 2ab plus b squared. And that have 2 times this times this. So I have negative 2 times cosine of x times sine of x times x natural log of x times natural log of x plus b squared, which is cosine squared x. All of that is divided by this x natural log of x squared. And x natural log of x quantity squared is the same as x squared times natural log of x squared. And all of that has to be multiplied by the natural log of x raised to the cosine of x power. Very, very long and tedious, isn't it? Let me see if I have any like terms. I don't see any like terms actually. I've got cosine of x terms here, here, and here. And of course here. I've got the x squared natural log of x squared there and there. And then this can be combined. We can call that sine of 2x if we want to. But it really doesn't simplify very much. Anyway, that's f double prime. Say, okay, well, what does that mean? Well, it turns out that the zeros of this function are points of inflection, provided that f double prime changes signs there. So I think what we'll do, what'll probably be easiest to do, is rather than trying to set these functions equal to 0, solve for x, and then creating a sign chart for those functions, and then using the sign chart to infer where the graph is concave upward or concave downward. We'll just use a graphing calculator. We're going to use Desmos.com to graph f prime and f double prime. We've done the computation by hand, so we know we're capable of doing it. But we aren't able to solve these for x, because they're not really simple functions that are easy to solve for x. When we set them equal to 0, that is. So we will just look at the graphs and know when they're equal to 0, because we'll be able to see when the functions are equal to 0. And then we'll use the signs of f double prime and f prime to infer relative extrema of the original function, to infer points of inflection of the original function. And all of those graphs, the graph of f, graph of prime, and graph of f double prime should all be consistent with each other, and they should all be telling the same story. So let's look at that. Let's look at those two graphs on Desmos.com. All right, so this is our function f of x equals natural log of x raised to the cosine of x power. We said that the domain was 1 to infinity. So when we compute f prime, we're only interested in that function on the interval from 1 to infinity. Oops, oh no. We computed f prime, we did that by hand. We used logarithmic differentiation. We said we can use f prime to infer relative extrema of the original function. Say, okay, well, how can we do that? Well, remember the zeros of f prime correspond to potential relative extrema. So I've got an x value here at x equals 2.03108. That's where f prime is 0. And then we've got another one at x equals 3.76136. And then we have another one, and then another one, and then another one. So we actually have 1, 2, 3, 4, is that 4, 5 points that correspond to relative extrema of the original function. So let's see what those points are, or let's type those points and graph them. This is 2.03108. And we'll plot the xy pairs. So I'll evaluate the function there as well. And if you want, you can evaluate the first derivative there. So we see that the first derivative is 0 at that location, and then the function value is that function value. The function value is that 1.165. You'd say, okay, well, f prime is changing from positive to 0 to negative at that location. Say, well, what does that mean? That means the original function is going from increasing to having a 0 slope to decreasing. So this should be a relative maximum. And we'll see that when we graph f in a little bit. I'm just choosing not to graph that right now. And then we will graph we'll do that for the other 1, 2, 3, 4 zeros. It's kind of boring, so I'm going to pause this. I'll let you do that as well. If you're on Desmos, I would highly recommend that you are on Desmos while you're watching this and doing your own calculations and making sure that you're getting the same results. Okay, so all I did while I had the recording paused was I typed in all of those ordered pairs here. So we said, okay, at this location, at x equals 3.76136, our first derivative is equal to 0, and our first derivative changes from negative to positive at that location. So the original function should go from decreasing to having a 0 slope to increasing. So I would expect a relative minimum at that location. Let's plot the corresponding point and label it. And then we know what the y value is. So this is a relative max because the function or derivative goes from increasing to decreasing. And then this corresponds to a relative min because the f prime goes from negative to positive, which means the original function goes from decreasing to increasing. I think I said that backwards. This one is a relative max because f prime goes from positive on one side, so it's increasing on one side, to negative on the other, so it's decreasing on the other. And this one is a relative min because f prime goes from negative, which means the original function is decreasing, to positive, which means the original function is increasing. So this is a relative max, and this one is a relative min. And then at this x value, f prime changes from positive to negative, so I'd expect a relative max. So the function is increasing, the original function is increasing, then it has a 0 slope, and then it's decreasing. Find the corresponding xy pair. And then here, f prime goes from negative to 0 to positive. So we expect a relative min at this x value. So let's plot the ordered pair.
So that's been
and then at this one, we've got a 0 there. So and f prime goes from positive to 0 to negative. So the function goes from increasing to 0 slope to decreasing. So we'd expect a relative max there. Okay. So that's what we expect. And of course, if we want to know what the ordered pair is, we can label that point. Okay, well, let's graph it now. And we're right. Relative max, relative min, relative max, relative min, relative max. So the first derivative is telling us what we would expect it to tell us. It's giving us that, it's essentially giving us that sign chart that we would typically create by hand on paper with pencil and paper. Because we're able to read that graph and infer that the f prime is either positive or negative on certain intervals. Because f prime is either positive or negative on those intervals, we know the original function is either increasing or decreasing. I'd say, okay, well, what else can we learn from the first derivative? Well, wherever the first derivative has relative extrema, so at this x value and this x value and this x value and this x value, then the original function should have points of inflection. So let's ignore the original function just for a moment and find those points of inflection. Now again, the points of inflection should correspond to zeros of the second derivative and relative extrema of the first derivative.
Okay, so infant is several years old.
So let's find those points. The x value there is 2.6664.
What's actually going on in the rates with all the different informations.
And I want the function value there to find that point of inflection. And I think I want to plot the points of inflection in orange.
And, you know,
and I think I might get rid of the labels on the relative extrema now, but I'll keep the points of inflection labeled this time. And now our next point of inflection should correspond to the next relative minimum or relative maximum of the original function. Since our derivative is decreasing until we get to this point and then increasing on this to the right of it, since the first derivative is decreasing, that means our second derivative is negative. So that means the graph would be concave down over on this side. And then when the first derivative is increasing, that means our second derivative is positive. So our graph should be concave upward. As we go from this point of inflection to the next point of inflection. So the next point of inflection should correspond to this x value, 5.44852. So we'll plot that point. Well, that xy pair is the x value and the corresponding value of f prime. We want the x value and the corresponding value of f. So we'll plot that point now. I'm trying to plot the points in order. It's 5.44 something, right? 44852. And we'll plot the corresponding x or the y value. And I want that in orange. We'll label it. And I think I want to get rid of the labels on those extrema. So I'm getting rid of the labels on the purple point. I think I lost one of my, oops. No, no, I don't. I have my, this is a relative max, a point of inflection, a relative min, point of inflection, a relative max. I expect a point of inflection in here, which corresponds to that x value. And then we'll do the same thing for that x value and that x value. Actually, I think I'm going to skip this one. I'm only going to go out to 13. I'm just going to go from x equals 1 to x equals 13 rather than going beyond 13. But we can see that at all of these extreme values, we would have extreme values of the first derivative. We're going to have points of inflection of the original function. So I'll pause this now. I'm just going to type in the ordered pairs. I recommend you do the same. Okay, so I've plotted those points of inflection. Let's graph the original function. And I think we see what we're supposed to see. All of the purple points are relative extrema as before. The graph changes. Sorry. It's like the grid is changing a little bit on us. There we go. Our points of inflection correspond to the relative extrema of the first derivative. And we can see that those points of inflection should also correspond to zeros of the second derivative. So let's graph the second derivative as well. That's something that we actually computed by hand. It was very tedious, took a long time. I typed it in, you can see like it just goes on and on.
Okay.
That's our second derivative, technically.
Great.
That's what the second derivative looks like. Okay, now let's analyze the second derivative. Second derivative is 0 here at 2.664. And we've got a point of inflection at the original function at 2.664. So that's good. And the original or the first derivative has a relative minimum there. And the second derivative goes from negative to 0 to positive at that point of inflection. So the original function should go from concave up, downward to concave upward on that, or at that point, and it does. Now the second derivative is 0 at this x value, this 5.44852. That was a relative extremum with a relative maximum of f prime. And that relative maximum of f prime corresponds to this point of inflection. Since f double prime changes from positive to negative at that x value, the original function goes from concave upward to concave downward. And this first derivative goes from increasing to decreasing. Okay, the next point of inflection comes when this second derivative is 0. It's at 7.4721. That corresponds to a point of inflection of the original function. That's good. It also corresponds to a relative minimum of the original function or the first derivative. That's good. The second derivative changes from negative to positive at that x value. So the original graph goes from concave downward to concave upward, which is what we see. We also see that the first derivative goes from decreasing to increasing, so that's consistent. And say, okay, well, when's the next point of inflection? It occurs at this x value, x equals 11.67961. That's the second derivative goes from positive to negative at that x value. So the original graph goes from concave upward to concave downward. And we see that f prime goes from increasing to decreasing. So all of that is consistent. And you might say, okay, how do we know that those are the graphs? How do you know we didn't actually make a calculation error? This is one thing that I hesitate to show my students because I don't want you to sort of use it to cheat and not actually know how to compute the derivatives by hand. Because most of the time when you're taking, Calc 1, Calc 2, Calc 3 differential equations, you actually need to know how to compute the derivatives by hand. But it turns out that Desmos sometimes can compute that derivative for you. So I'm going to hide that derivative now, first derivative, just for a second, and I'm just going to type f prime and ask it to graph it. And then I'm going to graph my f prime that I computed myself. And we see that my f prime and Desmos's f prime are the same. So I know I didn't make a computation error. I know I did that correctly, so that's cool. Now, the same thing is true with that second derivative. Desmos can compute second derivatives for us. So I'm going to type f double prime of x. I'm going to hide the second derivative from Desmos. And then I'm going to graph over my curve. We see that they're the same curve. So we did our calculations correctly. So, okay, let's say you didn't know logarithmic differentiation and you still wanted to know something about the graph of natural log of x raised to the cosine of x. If you didn't know how to compute that derivative, you could still use Desmos.com to graph natural log of x raised to the cosine of x, to graph f prime and f double prime. And then you could use these curves to infer something about the original graph, the graph of the original function. But if you're wondering, how do I get that formula for f prime or f double prime? That's when we would use that logarithmic differentiation. We see that our hand calculations are correct. And with the combination of the hand calculations and Desmos.com, we can analyze the function, use the first and second derivative to infer something about the graph of the original function. We could have used those to graph the function by hand, provided that we could graph f prime and f double prime by hand. We couldn't actually do that. But basically, we're just seeing that the derivative, the original function, the first derivative and the second derivative are consistent with each other. They're all telling the same story, and we know how to interpret them. F double prime giving us some indication of concavity and points of inflection, and f prime giving us an indication of when the function is increasing or decreasing, when the function has relative extrema. And we also notice that the relative extrema of the first derivative correspond to points of inflection of the second derivative, or points of inflection of the original graph and zeros of the second derivative. All right, I think that's it. Let me know if you have any questions about logarithmic differentiation. I think it's kind of cool that it's basically just a combination of that power rule and that rule for a to the x, where a is some base other than e. But yeah, we can use it for curve sketching. We can use it to find slopes of tangent lines. We can use it to find instantaneous rate of change if we had a function, a real world function that had a base that changes or an exponent that changes, or we have both of those at the same time. All of those we can do all of those computations with logarithmic differentiation. So I hope you like that new technique.